we started the electronic configuration, and we took the electronic configuration of both elements and ions of main group elements. But now we took also the electronic configuration of transition metals, or what we call them the D block elements. And now we want to find out how to write the electronic configuration for positive ions obtained from transition metals. So for example, let's start by, for example, iron. Iron has the electronic configuration, which is 1s2, then 2s2, 2p6, 3s2, 3p6, and then we said that we are going to leave 3d empty. And then we start by filling the 4s by 2 electrons, and then we have 6 electrons in the 3d subshell. Now, what if we have iron plus 2? When we want to write the electronic configuration of the positive ion of a D block element or a transition metal, since we filled the 4s first and then the 3d, also removing the electrons, we are going to remove the electrons first from the 4s and then from the 3d if we want to. So to write the electronic configuration of iron plus 2, we are going to remove the 4s electrons. How are you, Mawadda? I allowed you recording. So here, when we want to remove the electrons in the 4s, this is the first step, is to remove the electrons in the 4s. As we started by filling the 4s first before the 3d, also we remove the electrons from the 4s and then from the 3d. And so the electronic configuration of iron will be, iron plus 2, will be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d, 3d6 I mean. We don't have a 4s because we remove the electrons from the 4s before we remove it from the 3d. Okay, now what if we have iron plus 3? If we want to write the electronic configuration of iron plus 3, then we want to remove 3 electrons. So we are going to remove the first 2 electrons from the 4s, and then the third electron is going to be removed from the 3d. So we write the electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6. Now we remove 2 electrons from the 4s, and then we are going to remove an electron from the 3d, and we get 3d5. There's sometimes some students say that if I have iron 26 and then I want to form iron plus 3, for example, this means that we are going to remove the 3 electrons from the 26, and this makes 23 electrons to be distributed about the different subshells and shells on subshells. And this means that he's going to write 1s2, 2s2, 2p6, 3s2, 3p6, and then he starts filling the 4s by 2 electrons. These are 20 electrons, and so they put the 3 electrons left in the 3d, and this is wrong. This is wrong. Do not do so. Do not say that if I want to form a positive ion from the element, I remove, this is for transition metals. Maybe this is correct in other elements, but in transition metals, we do not do that because this will make us write the electronic configuration wrong. Because if you say that I have 26 electrons, so I'm going to remove 3, then there will be left 23. I'm going to distribute the 23 about the different shells and subshells. You have to fill the 4s before the 3d, so you are going to fill 4s2, then 3d3. This is wrong. Don't do that. Whenever you have a transition metal, write the electronic configuration of the metal in front of you, and then if you have a plus 2, remove the 2 electrons from the 4s. If you have a plus 3, you remove 2 electrons from the 4s and then 1 electron from the 3d. Understand? Let's have another example. If I have copper, for example, we said that copper is one of the exceptions. The electronic configuration of copper is 1s2, 2s2. Hello, ya Omar. I allowed you recording. 1s2, 2s2, 2p6, 3s2, 3p6. We said that we are going to fill the 4s before the 3d, but as copper is an exception, we said that this will be 3d10 and 4s1. We should write 4s2, 3d9, but we said yesterday that in order for copper to be more stable, its electronic configuration should be 3d10, 4s1. And this is an exception together with the chromium. Okay, so what if we have a copper +1 ion? If I want to write the electronic configuration of copper +1 ion, so here, as we said, since we added the electrons first to the 4s and then to the 3d, also we have to remove the electrons from the 4s before the 3d. So if this is copper +1, then the electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, and then we write 3d10 because we shall remove this electron from the 4s orbital to write the electronic configuration of copper +1. What if I have copper +2? Copper +2 means that we are going to remove 2 electrons. So this electron will be removed first, and then we have to remove one of the electrons in the 3d to become 1s2, 2s2, 2p6, 3s2, 3p6, and then we have 3d9 for copper +2. So in any transition metal, as we add the electrons first to the 4s and then the 3d, also on removing the electrons, we remove it from the 4s first and then the 3d. If you want another example, okay, Mavi, can you give me the electronic configuration of cobalt 27?
One S2.
Yes.
2s2.
Excellent.
2p6.
Yes.
3s2.
Yes.
3p6.
Yes. Which orbital is filled first?
We fill the 4s first.
Yes.
So
Excellent.
4s2.
Yes.
And then we have a total of 10, 12, 18, 20, and then 37.
Yes. Excellent. Okay. Then Rodina, if I have cobalt +2, what am I going to do? What is the electronic configuration?
1s2.
Yes.
2s2.
Yes.
2p6.
Yes.
3s2.
Yes.
4p6.
3p6.
6, sorry. Yeah.
Yes.
3d1.
And then?
I removed the 2 from the 4s2, so it's just
Yes,
3d.
excellent. We have to remove these 2 electrons, and we are left with 3d7. Okay. Abdurrahman, what if I want to form 3 cobalt +3?
1s2.
Yes.
2s2.
Yes.
2p6.
Yes.
3s2.
Yes.
3p6.
Excellent.
3d6.
Yes, excellent. So we removed 2 electrons from the 4s and we removed 1 electron from the 3d. Okay, you understand now how to form the electronic configuration of the transition metal ions. They're ions, not themselves. Do you have any question? Okay. Now, today we are going to start a new topic, which is the ionization energies. What is the ionization energy? It is the energy required. It is the energy required to remove an electron to remove an electron from a gaseous atom to form gaseous positive ions. Okay, so what does this mean? It is the energy, ionization energy. It's obvious from its name. Ionization energy means the energy needed to form an ion. And here it should be a positive ion. It is the energy required to remove an electron from a gaseous atom. It should be a gaseous atom to form gaseous positive ions. We have different ionization energies. We can have first ionization energy to remove only one electron. We have second ionization energy to remove 2 electrons, and so on. So if I have a sodium atom and it should be in the gas state, in order to remove an electron from this sodium atom to form a sodium positive ion in the gas state plus electron, we need what we call an energy that is called the first ionization energy. And we know, of course, that sodium is present in group 1, and so it needs only to remove 1 electron in order to have the full outer shell number of electrons like its nearest inner gas. This is by the first ionization energy. But if I have an element, for example, calcium, present in group 2, then it needs to lose 2 electrons to form the calcium plus 2 ion. But of course, it will not lose these 2 electrons in one step. But in the first step, it will lose only 1 electron in the gas state plus electron by its first ionization energy. And then the calcium positive ion in the gas state will remove the second electron to form the calcium plus 2 ion plus the second electron by the second ionization energy. So we have to write them in 2 equations like that. If they ask us what is the second ionization energy of calcium, they will give you choices. Among the choices, there will be calcium solid forming calcium plus 2 electrons gas, or they can give you calcium gas plus 1 to give calcium ion plus 2 gas plus electron, or they can give you calcium ion in the gas state to form calcium plus 2 gas plus electron. Of course, you have to choose this one. You don't choose the calcium solid forming directly calcium plus 2. You do not, sorry, what is this? I wrote this twice, isn't it? No. Here, for example, if we have calcium solid forming calcium plus 1 or whatever, calcium solid forming calcium plus 1, or even if this is a positive charge, it doesn't matter. But what we are going to choose is to choose the one having calcium positive forming calcium plus 2 ions in the gas state. You have to choose this one. You don't have to choose any other choice except that the calcium positive ion in the gas state forms calcium plus 2 in the gas state plus electron. So we call this the second ionization energy, and we call this the energy needed to remove 1 electron from the calcium atom in the gas state. Then we call this the first ionization energy. We don't have calcium solid at all, because it should be in the gas state from this definition. It is the energy required to remove an electron from a gaseous atom to form gaseous positive ions. Okay, now ionization energy was used to prove that the structure of the atom, in the structure of the atom, we have different energy shells. One of the ways they proved that the atomic structure means that we have a positive nucleus in the middle and we have different energy shells around this nucleus was by using the ionization energy values. Now, how can we do that? We said here that sodium would like to lose only 1 electron to be more stable or to have the electronic configuration of the nearest inner gas. But we can remove all the electrons present in sodium by what we call successive ionization energies. It means that by one ionization energy after the other, we can remove all the electrons present in sodium. So if we look here at the sodium atom, we know that the sodium has 11 protons, and so it has 11 electrons. If even we write it in the simplest form, electronic configuration 281, it means that in sodium, we have 3 shells around the nucleus. This is the nucleus. We have the first shell, we have the second shell, and we have the third shell. Okay, so we have this positive nucleus. We have 2 electrons present in the first shell. We have 8 electrons present in the second shell. And we have 1 electron present in the last shell. Now, which is easier to remove? The electron that is very near or very close to the nucleus, or the electron that is in the outermost orbit, or we call it the valence shell? Which is easier? Which needs less amount of energy? What do you think, ya Mawadda?
Yes, can you repeat the question?
Which is easier to remove? Which needs less amount of energy to remove an electron?
Yeah.
Because ionization energy means removal of electrons. So which is easier, to remove an inner electron or to remove this outermost electron?
The outermost electron.
Yes, excellent. Also, Heba told me outermost, and Abdurrahman said the outermost. Yes, and Mavi said the outermost. Yes, excellent. So all of you are excellent. It's easier to remove this electron because, as you see, that this electron is further away from the nucleus, and this means that the attraction force between this electron and the nucleus is the least. This is the least amount. We need the least amount of energy to remove this electron because it is the furthest away from the nucleus. So if, for example, this is the value of the ionization energy needed to remove this electron. We had in the sodium atom, we had 11 protons and we had 11 electrons. Now, when we remove this first electron by the first ionization energy, which is this value, we find that we have still 11 protons and now we have 10 electrons. Now, we want to remove this second electron. I want to remove this second electron. So what do you think, Yaheba? Will it need a much more energy to remove this electron, or the same energy to remove the outermost electron, or maybe similar energies to remove this electron?
I think it needs more energy because it's in the second energy level.
Yes, excellent. Hiba said that it will need a much more energy to remove the second electron. Yes, excellent, Yamavi. It needs a much more energy to remove this second electron than to remove the first, because as you see, we went from a shell to an inner shell in order to, now this electron was removed. And then this second shell is closer to the nucleus. It has a distance that is closer to the nucleus, and this means that the attraction force between this electron and the nucleus will be higher than that between this outer electron and the nucleus. And this means that we need a much more energy to remove this electron than to remove that electron. And here in the ionization energies, we'll find that there will be a jump in energy. A jump in energy means that we have much more energy to remove this second electron than the first electron, because of two reasons. That this electron came closer, is at a shell that is closer to the nucleus. And the second thing, that now 11 protons are attracting 10 electrons. And of course, when 11 protons attracts 10 electrons, they will pull them more, or they will attract them more to the nucleus. Because like when you play, I usually say this, if you have, you know the rope play, that you have a team here and you have another team here, and they are pulling the rope. If you have here 11 electrons in a team and 11 protons in a team pulling each other, and the rope is at a certain place, it should be in the middle between them. But when one of these team leaves and you have 10 persons instead of 11, and here we have the same 11 protons, which are the same number of persons in the team, they can pull these 10 electrons more. They can pull them towards themselves because they are stronger. Their number is greater. So they can pull these 10 electrons more than the 11 electrons at the beginning. So we have two reasons here that the energy is higher, much higher than that needed to remove this outer electron, because this electron is an inner shell, which is closer to the nucleus than the outer one. And the other reason is that we have now 10 electrons to be pulled by the 11 protons. Okay, understand? Now, to remove the third electron, what do you think, Rudaina? Will it need a very much high energy to remove more than the second electron, or a nearer energy, or the same energy?
Nearer energy.
Yes, excellent. It's a nearer energy. Why?
Because it's the same energy level, but it's easier to remove it than if it was in a different energy level.
Yes, we will say that since it is in the same. Yes, Yamavi, excellent. Since this electron is present in the same energy shell as the second one, so it will need, maybe someone will say it will need the same amount of energy because it's at the same distance away from the nucleus. Yes, that's correct. But you should remember that here we have 11 protons pulling now 9 electrons instead of 10. And this means that these 9 electrons left, are pulled by the protons more than the 11 protons pulling 10 electrons. So the third energy to remove the third electron should be higher than the first, should be higher than the second, but not too much higher. There was no jump because both of them are present in the same shell. Okay, understand? Omar, what do you think? I want to remove now this fourth electron. Will I need a very high energy to remove it, or a similar energy, or maybe a little more energy than to remove the third? Yes, ya Omar?
We need a similar energy because it is in the same energy shell.
Okay, you may think that it is similar because it is in the same energy shell, but you do not remember that here we have 11 protons pulling 8 electrons, not only 9, isn't it? And we said that the less number of electrons, they are going to be pulled more towards the 11 protons. Remember this rope game, that whenever you have more persons to pull less number of persons, they are going to pull them more towards themselves, isn't it?
Yes, yes.
So this means that we need, yes, a little bit higher energy, not too much higher, but it's higher than removing the third electron. Okay, understand? Abdurrahman, what do you think about removing this fifth electron? Will it need similar energy as these electrons present at the same level, or much high energy, or a little bit more?
It will need a little bit more than the one by its side because it's in the same place, but there is more protons than electrons.
Yes,
There's
it's
more
in the
attractive
same
energy.
shell. Excellent, Abdurrahman. It's the same shell. So it's at the same distance away from the nucleus, but it will need a higher energy since we have now less number of electrons being pulled by the same number of protons, which are 11 protons from the beginning. So this means that we will need a higher energy, but not too much high. And so will be to remove these other 4 electrons. To remove every electron in the 8 electrons in the second shell, we need higher and higher energies, but not with a jump, because all of them, 1, 2, 3, 4, 5, 6, 7, 8, all of them, as you see, needs higher energies, but not with the jump. We do not need a very high energy to remove one of the electron after the other, because all of them belong to the same shell. They are at the same distance away from the nucleus, but the only factor here is that in every removal of 1 electron, the number of electrons becomes lower by 1, but the same number of protons, and this means that they will pull the electrons by more energy. Okay, now we finished removal of these 8 electrons in the second shell. Now we will start to remove the electrons that are present very close to the nucleus. And this means that whenever, as they are very close to the nucleus, so what do you expect, Yamavi? Do we need a very much higher energy to remove them, or similar to those in the second shell?
No, there will be a jump because it requires more energy. It's closer to the nucleus.
Yes, excellent. We have here the first reason, as Mavi said. Now, this shell is the closest to the nucleus. So these two electrons are the strongest electrons attracted to this nucleus. They are the closest. There is nothing in between them and the nucleus, so they are very much attracted to the nucleus. And at the same time, we have 11 protons attracting 2 electrons only, which means that they pull them very strongly. So in order to remove any one of these 2 electrons, we need a very, very high energy to remove them. That's why you will find here that there is a very big jump to remove these 2 left electrons. We need a very big jump from the electrons to be removed in the second shell, because they are the closest to the nucleus. They are very near to the nucleus. Nothing is in between them and the nucleus. And at the same time, we have 11 protons inside the nucleus of sodium, pulling 2 electrons only. So this is the strongest attraction force. So if we look at what we call this, we call it the successive, we call this the successive ionization energy of sodium. Successive means that one after the other. To remove all the electrons present in this atom of sodium, we needed these different amounts of energies. And from this successive ionization energies, we can say that sodium atom is present in group number 1 from the number of energies. So here, if we draw the successive energies against the number of electrons to be removed, if this is the ionization energy against the number of electrons to be removed, we will see that we needed a certain amount of energy to remove the first electron, and then there was a jump. Whenever we have a jump between the first electrons to be removed and the next, this means that we can find out the number of the group of this atom or of this element. So here, sodium, we had only 1 ionization energy, after which a big jump took place. This means that sodium belongs to group 1. So from the number of ionization energies before the first jump, we can determine the number of group of this element. For example, if I have two energies and then a big jump, and then the 8 electrons, the 8 ionization energies, 1, 2, 3, 4, 5, 6, 7, 8, and then another jump, and then 2 electrons. This means that this element belongs to group 2, because there was 2 ionization energies before the big jump. This means that this element belongs to group 2. If we have 3 ionization energies nearer to each other and then a big jump, then this means that this element belongs to group 3, and so on. If I have 5 ionization energies close to each other and then a big jump, this means that this element is present in group 5. So from the number of ionization energies before the first jump will give us the number of the group of this element. Okay, understand? This means that in the outermost shell, we have 5 electrons to be removed. In the outermost shell, we have 5 electrons to be removed. That's why it took 5 different ionization energies. They should be one of them more than the other, but they are near to each other before the jump in order to remove the next electrons that are present in the second shell. So we have to remove these 5 electrons before removing the electrons present in the second shell. That's why we got 5 nearer ionization energies and then a big jump when we want to remove the electrons present in the second shell. Understand me? So from the number of ionization energies before the first jump, from it we can get the number of group at which this element is present. If we look at the successive ionization of sodium, we can also notice that there are three sets of ionization energies. By set, we mean ionization energies that are nearer to each other. If you look here, you will find that there is an ionization energy and then a jump, then 8 ionization energies, then a jump, then 2 ionization energies. We say that this is a set of ionization energies. This is another, this is a third, between which there are jumps in ionization energies. So if they give us the successive ionization energy, we can also determine the number of the period at which this element is present. So from here, we can say that sodium belongs to group 1 because it has only one ionization energy before getting the jump. And then since we have 3 sets of energies, then sodium is present in period 3. We have 1, 2, 3 sets, so it belongs to period 3. So in this way, by using ionization energies, we can determine the position of any element in the periodic table. Of course, we are talking about the main elements, not the transition ones. So by using the successive ionization energies for any atom, for any element, we can get its position in the periodic table, which group and which period. Okay, do you understand or do you have any question? If you have any question, please ask. Type. Okay, let's see how there is a jump. How do we get jumps in ionization energies? To see the numbers here, for sodium, for example, this is the ionization energy for sodium. We will see that here, we have the first ionization energy. This is the first ionization energy. It is about 500 kilojoules per mole energies. The units of energies are kilojoules per mole. You will see that here we have 500, nearly 500. And then there was a jump from 500 to 4,563. There was a jump by 4,000 units. So here, if we compare hundreds with 4,500, this means that there was a jump from 500 to 4,000. Whenever we were at 100 units or at 100 numbers, and then we have thousands, this means that we have a jump. So this is the first jump from 496 to 4,563. This is a jump. Now, if we look here between 4,500 and 6,900, the difference is about 2,500. We do not consider this a jump. Why? Because this value is in thousands. So if a difference is also in thousands, we do not consider it to be a jump. Here we have 4,563, and here we have 6,913, about 2,500 difference. We do not consider a jump because this second ionization energy was 4,000 by itself. Here we consider this a jump because this number was in hundreds and we got 4,500. So this is a jump. Okay, understand? Now, if we look here between 6,900 and 9,500, there is a difference in energy, which is about also 2,000 or something like that, 2,500 maybe, or maybe, yes, about 2,600 maybe. This is not considered a jump. You see here, there are no jumps. Yes, the energies are greater. One after the other, they become greater and greater, but there is no jump. Why there is no jump? Because we are comparing thousands by thousands here from 9,500 to 13,300. So the difference is about 3,000. It's not considered a jump. Here between the 5th and the 6th, the difference is about 3,000. It's not a difference. If we compare between the 6th and the 7th, it is about 4,000, not considered. 5,000, not considered. 3,000, not considered a jump. But now look here between the 9th and the 10th. Here we have 28,000, maybe you can even approximate it to 30,000. and then it jumped to 140,000, from 30 to 140. This is a very big jump. From 30 to 140, this is a very big jump. You compare it with this increase in energies, in ionization energies. They were only 2,000, 2,500, 3,000, up till 5,000. It's not considered a jump. But from 28,900 to 141,000, this is a big jump. You see, this is a big jump here, which means that we go from one energy shell to an inner shell. Since we have a much increase in energy, this means that we are leaving one energy shell and going to an inner shell closest to the nucleus. And so the attraction force between the electrons and the positive nucleus is so high, and we need a very high energy in order to remove this electron. Okay, you see how we get the jumps, because sometimes they give us tables and they say from this table predict the number of group of that element. So you have to see the jump. Of course, they not always give us all the successive ionization energies. Sometimes they give us only 5 of them or only 6 of them. But from the jump, we can determine at which group is this element belonging. Okay, understand? Okay, you will see here that they plot log ionization energy against the order of electron removed. They do not plot the ionization energy against the number of electrons removed. They plot the log. And sometimes they ask you such a question: why do we plot log ionization energy against the number of electrons removed and not the ionization energy itself? So what are you going to say, Abdurrahman? You know what's the log?
The number, 1, 2,
it's a mathematical function, isn't it?
Oh, yes.
Okay. So why do you think, Abdurrahman, they plot log ionization energy and not the ionization energies themselves?
Because the ionization energy itself is so big.
Yes, excellent. Because there is a wide range. Yes, excellent, Yamavi. There is a wide range between the values in the ionization and the successive ionization energies. You should start by, you should divide this part between values from 500 to 160,000. How can you do this? How can you divide this part from 500 till 160,000? It's impossible. It's something, or else you will get very, very close values at a place, and there is a very big place between two others. It's impossible to draw. There is a wide range of values for the successive ionization energies, makes it impossible or makes it not good to draw as a graph here. So we have to use the log values, because if you take at your calculator and you say log, if you take log, for example, this value, which is 9,544, I got 3.97. It means about 4. This is 4. So the value is reduced from 9,500 to 4. If we take the log 496, we get a value of 2.7. So we start by a value of 2.7. This is 4. If I take this value, which is the greatest one, log, for example, 160,000, we get a value of 5.2. You see, we have small values, not 160,000, not 140,000, not 16,000. We get small values starting from 2.7. We draw starting from 2.7 up till 5.2. If we take the greatest value, it's between 2.7 to 5.2. So you can arrange your numbers here. You can arrange the values, the small values, in a plot. But since the ionization energies themselves are very big numbers, so there is a wide range between the numbers, so you cannot arrange them on the y-axis. Okay, understand what I mean? So always we draw log ionization energies against the order of electrons removed if we are dealing with successive ionization energies for one element. This is only for one element. Okay, do you have any question? Okay, now we want to see what is the trend in the first ionization energies. What are the trends? What are the trends? In the first ionization energy down a group. We want to see what is the trend in the first ionization energy down a group. Let's take group 1 as an example, and all what we are going to say about group 1 will be said about all the other groups. For example, if I have lithium, sodium, potassium, rubidium, and cesium, we know that lithium is present in period 2, sodium is present in period 3, potassium in 4, rubidium is in 5, and cesium in 6. This means that if we look at lithium, it has 3 protons, then we have 3 positive charges, and then we have 2 other shells to be filled. This shell is filled by 2 electrons, and this shell is filled by an electron. When I draw this arcs, it means that this is a complete shell. But for simplicity, I draw it as an arc. Okay, but this means shells. These are the shells around the positive nucleus, but just to draw them in a simpler way. Now for sodium, we have 11 protons and we have 11 electrons, and these electrons will be arranged in the form of 2, 8, 1. But I mean that since all of them belongs to group 1, then we will have only 1 electron in the outermost shell. For potassium, we have 19 protons, and we have 1, 2, 3, 4. Potassium is present in period 4, which means that we have 4 shells to be filled. And the last shell, since we are present in group 1, the last shell will have only 1 electron in its outermost shell. For rubidium, I really do not remember how many positive charges are here, but maybe 35 or 36, something like that. And then since it is present in the 5th shell, this means that it will fill 5 shells. For cesium, it will fill 6 shells because it is present in period 6. So we have down a group, we will see that as more number of protons are present, there are more number of electrons, they will fill more number of shells. Of course, all these shells are filled by electrons. All these inner shells are filled by electrons. Now, we want to study the trend in the first ionization energy. It means the removal of the first electron in the outermost shell. We want to see what is the trend in removal of these outer electrons. So what happens down a group? Do you expect the ionization energy to increase or to decrease, ya Omar? What do you expect for the ionization energy? Do you expect it to increase or decrease? By other means, is it easier to remove this electron in lithium, ya Omar, or to remove this outer electron in cesium? Yes, excellent. Omar said, or Abdurrahman said that down a group, the ionization energy decreases. The ionization energy decreases. It means that in order to remove this outer electron from cesium, we need less amount of energy to remove this outer electron in lithium. Do you know why, Mawadda? Do you know the reason? Why it is easier to remove this electron in cesium than to remove this electron in lithium?
Because it's like farther away from the nucleus.
Yes, excellent. Excellent. This is a reason. It's a very important reason. Mawadda said because this electron is further away from the nucleus, and so the attraction force between the positive nucleus and this electron is the weakest or is the least. That's why it requires only a small amount of energy to remove it. This is one reason. Excellent. But when they ask you such a question, state and explain the ionization energies down a group, you have to say 3 reasons. Yes, Rodina, excellent. We have to say 3 reasons. Now, we always will say that, of course, we are going to say that the ionization energy, when they say state and explain, the first thing to say is that ionization energies decreases down a group. Why? Explain. Everything here needs explain. So the first thing you say, although the positive charge increases, the positive nuclear, we can say the positive nuclear charge increases. What do we mean by the positive nuclear charge? It means the number of protons inside the nucleus. We see that as we go down, maybe this is, I don't remember, this is 35 or 36, something like that. So as you go down the group, you will see that the positive charge increases, the positive nuclear charge increases, and when the positive charge increases, we would expect that the attraction force between this increasing positive charge and the electrons will increase. The attraction force increases. It's correct. Really, the attraction force increases. As the nuclear charge increases, the attraction force between the nucleus and the electrons will increase. But we have 2 other factors outweighing this increase in positive charge. We have 2 other factors. The first factor is that, as Rodina said, that the distance between the outer electron, the outermost electron, or we can call it the valence electron, and nucleus increases. And nucleus increases. And the third factor, as Rodina told me from a moment, that the shielding effect increases. The shielding effect increases. What is the shielding effect? Shielding means that something shields the effect of one thing from the other. Shields means in Arabic حاجز. في حاجز. There is a shield, there is something in between. There are something between the positive nucleus and the electrons. What is this something? It is the electrons that are found in the inner shells. In inner shells, we have electrons. Of course, there are a number of electrons. Here we have only 2 electrons, so the shielding effect is small. But here we have 2 electrons and then 8 electrons. The shielding effect increased because the number of electrons in between this positive nucleus and the outer electron, it increased. The number of electrons increased. They will shield the effect of the nucleus from the electron in the outermost shell. It means that as if they are not seeing each other. And the more the number of electrons in between the positive nucleus and the outer electron, the more they will not see each other. They cannot affect each other. The effect between the positive nucleus and the electron will decrease. We call this the shielding effect. Like 2 persons. If 2 persons were talking in front of each other, they can see each other very well. They can talk to each other and see each other very well. But if we put a curtain in between them, they still see each other, but not like before. This curtain is the electrons that are in between the nucleus and the outer electron. If I put 2 curtains, what happens? They cannot see each other like before, and not like this case when there was only 1 curtain. If I put a 3rd one, a 4th one, a 5th one, the more I put curtains, the more these 2 persons will not see each other and they will not be affected by each other. They cannot talk, they cannot see each other. So their effect on each other will decrease. That's what happens here in the atom. If I have in cesium, I have this positive nucleus, 1 person, and this outermost electron, the other person. I placed here 1, 2, 3, 4, 5 curtains in between them. They are shielding the effect between these 2. So the more the number of inner shells, the more will be the shielding effect. Shielding effect means that the nucleus will not any longer affect this outer electron. So although the positive charge increases down the group, we were expecting that this positive charge will attract the outer electrons strongly, and this means that we need a high energy to remove this electron. But we have two other factors that outweigh the first factor. We say so. There are two other factors that outweigh the first factor, which are the distance between the valence electron and the nucleus and the shielding effect. Both increases, and so the attraction force between the positive nucleus and the outermost electron decreases, and it requires less amount of ionization energy to remove this electron. Okay, do you understand, or do you have any question? Of course, what we say about group 1 will be said about group 2, will be said about group 3, group 4, group 5. Whenever they ask you about any group, you say the same thing. You say the same answer. This question will have either 3 or 4 marks. So you have to say these things, that the ionization energy decreases down a group, you get a mark. And then you say these factors, you get the other marks. Okay, do you understand? Type. What happens across a period? We now want to study the trends of first ionization energy across a period. Also, when we study a period, this means that what is going to be said about this period is also going to be said about others. So let's take, for example, period 2 and see what happens. In period 2, we have lithium, we have beryllium, we have boron, carbon, we have nitrogen, we have oxygen, fluorine, and neon. All of these belong to period 2. And what do we mean by the word period? It means how many shells are going to be filled. What do you think, Erudaina? How many shells are filled in period 2?
2 shells.
Yes, excellent. We have 2 shells. Excellent, Yamab. We have 2 shells filled. So in lithium, we have 2 shells. In beryllium, 2 shells. In boron, 2 shells. Carbon, 2 shells. Nitrogen, 2 shells. Oxygen, 2 shells. Fluorine and neon, all these are going to fill 2 shells only because they belong to the same period. But here, the positive charge is +3 for lithium. For beryllium, we have +4. For boron, we have +5. For carbon, +6. For nitrogen, +7. For oxygen, +8. For fluorine, +9. For neon, +10. So the nuclear charge increases, or the positive protons in the nuclear charge in the nucleus increases. And electrons, when they fill here in the last shell. We have here 2 electrons filled and then 1 for lithium. For beryllium, it's 2 and 2. For boron, it's 2, 3. For carbon, it's 2, 4. For nitrogen, 2, 5. For oxygen, 2, 6. For fluorine, it's 2, 7. And for neon, it's 2 and 8 electrons in the last shell. So what do you expect, Yamavi, for the ionization energy across a period? Will it increase or decrease?
It'll increase because we have more protons pulling onto the valence electrons. Hence, there is a greater attraction between them.
Yes, excellent. Across a period, as Mavi said, the ionization energy increases. And she explained, because everything here in AS, they are going to ask you to explain why. Why did you say so? So as we go across a period, the ionization energy increases because as we go across the period, the nuclear charge increases, the positive charge inside the nucleus increases, and we are filling the same shells. So it is the same shielding effect. So the number of protons increases across a period, number of protons increases, and we have same shielding effect. Same shielding effect. The number of electrons that shield the effect of the nucleus from the outermost shell is the same, because in all of them, we have only one shell filled by 2 electrons, and then the second shell where we add more number of electrons. So they have all the same shielding effect. They only have only one shell containing 2 electrons that shield the effect of the positive nucleus from the outer electron to be removed. So the attraction force increases as we go across the period. The attraction force between the positive nucleus and the outer electron increases. And since the attraction force increases, it will require more energy to remove the outermost electron. Okay, so this is, we call this a general trend. We call this a general trend for the first ionization energies across a period. This is the first, this is a general trend. But inshallah, next time we will see that we have exceptions across a period. We have exceptions between group 2 and group 3, and between groups 5 and group 6. We have exceptions. Although it was expected for boron to have a higher ionization energy than beryllium, yet we will find that beryllium will have a higher ionization energy than boron. And between groups 5 and 6, it was expected for oxygen to have a higher ionization energy than nitrogen. It's the opposite. We'll find that nitrogen has a higher ionization energy than oxygen. And of course, this question, you will find that in most of the exams, they will ask about these exceptions, whether between groups 2 and 3 or between groups 5 and 6. Okay, so inshallah, next time we'll study about these exceptions. Do you have any question for today? Any question? Okay, thank you so much. Inshallah, see you.